Analytical Chemistry 1, Lesson Titration by Spreadsheet. Now, we've usually calculated titration curves with a different set of calculations depending upon the region we were interested in. At the beginning, before the equivalence point, at the equivalence point, and beyond the equivalence point. The calculations are based on choosing a volume of added titrant, considering the chemical reactions that will ensue, and determining the pH of the solution that results. Well, we will develop here a more general approach that is applicable at all points of the titration curve and is amenable to setting it up in a spreadsheet. Now, this is mainly a derivation. Follow it along as a means of convincing yourself that it is meaningful and that there are no approximations except for activity coefficients. The conclusion should be pretty easy to implement in a spreadsheet. We will first do this derivation for the case of titrating a weak acid with a strong base. We will ultimately see that the final result is readily translated to any other experimental condition. Here are the variables and constants we will employ. For the weak acid HA, we need to know the initial volume and the initial formal concentration of the acid. We will also need to calculate the formal concentration at any given point in the titration, and this is just a dilution calculation due to the added volume of titrant. So the weak acid is the analyte in this experiment. The titrant is the strong base. We will abbreviate it as BOH. We will need to know the concentration of the titrant base. Now, this is the concentration in the burette, not what might be happening in the beaker in which we are titrating. We will also need to calculate the volume of added titrant at any point in the titration. Now, the titrant volume is the variable that is changing. Usually we think of it as the independent variable. We choose its value and then find out how the chemical system responds to that added reactant. In this case, however, you will see that we view this as the dependent variable. The volume of added titrant is what our process will calculate. So B is the counterion to the hydroxide forming the base. Its concentration in the titration vessel at any point in the titration arises from the amount of added base divided by the total volume. Recall that VBOH is the variable in this. The other terms are all parameters that are constants specific to the details of the experiment. We will also need an expression for the weak acid's conjugate base concentration. Now recall the fraction of dissociation expression. Additionally, recall what the formal acid concentration is at any point in the titration. It is just a dilution issue. The moles of HA there were present originally divided by the current total volume. So by definition, the conjugate base concentration at any point in the titration is the fraction dissociation times this formal concentration. Now, write down the charge balance equation. Substitute for the two expressions we have just derived. Now, while this is a messy looking equation, it has some real virtue. The dependent variable is the titrant volume. The other formal concentration and volume terms are all constants for the problem. Hydroxide is related to the hydronium through Kw, and the alpha expression depends on constants and the hydronium ion. Basically, we have an equation with all the right terms. All we need to do is rewrite it. We could try to solve for H+, but we've already found that that leads to higher order polynomials requiring numerical methods to solve them. Instead, we will try to solve for VBOH. The denominators are the same, just the diluted volume. We can multiply them up and at the same time bring the hydronium and hydroxide terms together. Multiply out the volume terms, but keep the hydroxide and hydronium together. Gather the terms in the base volume on one side and the terms in the acid volume on the other. Factor out the volume on each side. Factor out the concentration on both sides. Rearrange it in this fashion. Now let me explain why we do it this way. The expression on the left-hand side is being called phi. Look carefully at the numerator and denominator. The only variable is the volume of added titrant, the VBOH term in the numerator. The others are all constants. The denominator is the number of moles of weak acid in the titration. The numerator is the number of moles of added base at that point in the titration. When moles of acid equals moles of base, we have reached the equivalence point by definition, and at that point, phi equals 1. Phi is the fractional distance to the equivalence point. We will start at 0 and increase to 1 at the equivalence point. Before the equivalence point, it will be less than 1. After the equivalence point, it will be greater than 1. The grand conclusion is that we can just rewrite this to solve for VBOH. So look at phi. It consists of two equilibrium constants, Ka and Kw, and the two initial concentrations, that of the weak acid and that of the strong base. And it has the hydronium ion concentration that shows up in 5 different places. So how do you use this? Well, instead of choosing a titrant volume and finding a resultant pH, you choose a pH. Find the titrant volume needed to reach that pH value. So this is why I say that this approach turns the problem on its head. But notice that no approximations were made in reaching this equation, and it is applicable from the beginning through the equivalence point and beyond into the post-equivalence point region. So computer assignment 3 is basically seeing if you can code this equation and the ones like it into Excel and generate a nice, smooth titration curve. The top equation on this page is perhaps the key one. In some form, it will show up again and again for all kinds of titrations. The challenge each time is to determine phi. Its form will change as the type of titration changes, but the structure and symmetry will be there. Finding phi for each type of titration is the key. Each can be derived as we have done it here, but I provide instead the conclusions without proof. Look at the titration of strong acids or bases with strong bases or acids. We obtain the following expressions. Look closely at the details and the symmetry of the equations. To use this in your spreadsheet, create a column of pH values. You want them close enough together to make for a smooth titration curve, but not so close together that it makes for so many points that it becomes unwieldy. Remember that the pH changes slowly through the buffer region. A lower density of pH values could be used here, but near the equivalence point, the pH changes rapidly with very small changes in titrant volume. Larger steps in pH are appropriate in this region. Most titrations we encounter involve a weak analyte and a strong titrant. Note how the 1 in the numerator is replaced with the fractional composition expression. It itself is pH dependent. I've written it separately to give you the start of an idea of how to split this up into separate computational steps rather than a single long, confusing, error-prone equation. In the case of the base, the fractional composition uses the same acid dissociation constant. If your data gives a base association constant, you need to convert it to the acid dissociation version. And we can write this out for the diprotic expressions as well. Note how we need to use 2 fractional composition terms, and the second one has a 2 times multiplier. Not surprisingly, you can see how the expression in the case of a weak diprotic base, analyte, has a similar form. Recall that the terms are structured to use the equilibrium constants in their acid dissociation form. Now this can continue for triprotic and tetraprotic, etc. There's the same general expression, but just with more fractional composition terms. And we know how to write the increasingly complex but very well ordered fractional composition terms. I won't write down any more. But we can also craft these expressions where both the analyte and the titrant are weak acids or weak bases. In those cases, the 1 in the denominator is replaced with fractional composition terms, just like in the numerator, except that they are for the titrant. We've also worked through how to calculate precipitation titrations. For brevity, I am only including here that where the stoichiometry is 1-to-1. I did give the equation for a 1-to-4 stoichiometry back in lesson 45, and the full derivation of this 1-to-1 expression was given there also. This equation is set up so that either the metal or the ligand can be the titrant, and the converse for the analyte, of course, and I think this is pretty straightforward. Finally, we include the equations for an EDTA titration. The equations hold for any 1-to-1 ligand-metal interaction, which is the case for our EDTA titrations. However, it is applicable to other ligand-metal systems as long as the stoichiometry is 1-to-1. We can derive for other stoichiometries, but they're not given here. First, we have it for metal as the analyte and the ligand as the titrant. Again, pick a value for PM, the minus log of the M concentration, the metal concentration. Substitute for the metal concentration. Find the titrant volume to reach that point. Note that when the ligand is EDTA, and that will often be the case for us, you use the conditional formation constant, as the pH will be fixed by a buffer at some value, and that needs to be specified in the problem. If the role of ligand and analyte can be reversed, we just have to take the inverse of phi for the new phi and switch the roles in the first equation. So here are the equations you can use to quickly create accurate, approximation-free, except for activity coefficients, titration curves. If you need more complex ones, I suspect that you will now be able to derive those expressions on your own. Good luck, and no, you wouldn't have to derive it on an exam.